and sharing the screen. And whoops. Today we're going to look at more equations. Last class we had looked at equations of a higher degree, radical equations, and equations with rational exponents. Today we're going to look at equations that are quadratic in nature and also absolute value equations. Then after that, we're going to start looking at inequalities, reviewing what we had done with interval notation, going over the rules for inequalities in terms of addition, subtraction, multiplication, and division. And then we're going to start solving compound inequalities. And hopefully we'll have time to start looking at absolute value inequalities. 1.45 on the quadratics is due by the end of the day today. 1.6 on those other equations are due up by the end of the day on Thursday. 1.7 are the inequalities. That'll be due on Tuesday, as will problem set 2 be due on Tuesday. Your next test will be available from end of class time Tuesday till midnight Wednesday. It'll be in my labs and you'll have to submit your work in Blackboard. Before we get started, does anybody have questions on any of that? Or does anybody have questions on anything from any of the homework? Does anybody want me to pull up my labs and look at any of those problems? Not hearing any questions then? Let's start looking at equations that are quadratic in nature. And what do we mean by that, quadratic in nature? They're not really quadratic equations, but they kind of fit the format. If we look at the idea of a general quadratic, we had said that a general quadratic was ax squared plus bx plus c equals 0. A, b, and c are real numbers, and x is a variable. What we notice is that it's a trinomial. It's in descending order. We've got one side 0. We've got a constant term. And if we compare the two variable terms, do you notice that the higher degree exponent is twice the other exponent, double the other exponent? And so if we can find an equation that fits that format, we'll say that it's quadratic in nature. And the way in which we'll solve them is we'll use substitution. Which is the idea of introducing a dummy variable that we'll solve for in the quadratic, and then work backwards to solve for the original variable. So let's start with a pretty basic example. Let's start with something like 4x to the 4th is equal to 13, x squared minus 9. First thing we want to do is make one side 0. And I think we've noticed that when we're solving an equation of any degree, it's usually easiest if that highest degree term is positive. So to make one side 0, I'm going to subtract the 13x squared from both sides and add the 9 to both sides. That gives me 4x to the fourth minus 13x squared plus 9 equals 0. Now that it's in descending order, notice that we have a trinomial. One side is 0. We've got a constant term. And when we compare the two variable terms, one exponent is twice the other. So what we're going to do is we're going to substitute. Usually you use u, which is a dummy variable, for the variable part of the lower degree term, or the variable part of the middle term. So we're going to define this new variable. So I'm going to say let u equal, and the variable part of the middle term is x squared. And now if u is x squared, u squared would be x squared squared would be x to the fourth. And so now wherever there is an x, we're going to replace it with something in terms of u. X to the fourth is u squared. X squared is u. And then we've got that 9. That gives us a quadratic equation that we'll solve. So we'll solve the resulting quadratic. And when I solve that equation, again, we've got four choices, I apologize. We could use the quadratic formula. We could use the completing the square. But again, I only like completing the square if I can make that leading coefficient 1 and that middle term is even. We could use the square root property. But with this one, I don't really have one side just being a quantity squared. Or we could factor. Looking at this one, I think it's a relatively easy factor. If I look at my 13, well, since 13 is the sum of the 4 and 9, if I make one for u and u, and the other 9 and 1. Signs are the same, both minus. If I check by FOILing, my outer would be minus 4u, my inner would be minus 9u, so that gives me that middle term of negative 13. So now it's factored, one side is 0, which means that one of those two factors is going to equal 0. On the left, where I have 4u minus 9 equals 0, I'll add 9 to both sides. It gives me 4u equals 9. And then I'll divide by 4 to get u equals 9/4. And the other one, I'll add 1 to both sides. And I'll get u equals 1. And so we've solved for u. But there's a problem here. We solved for u. Our original equation wanted us to solve for x. So what we're going to do now is we're going to back substitute. The definition of u to solve for the original variable. And so what does that mean? Again, way up there, we defined u to be x squared. So let's replace u with x squared. X squared equals 9/4, or x squared equals 1. Now we can solve. I'd use the square root property and get x is equal to plus or minus the square root of 9/4. So we get x is 3/2 or negative 3/2. And here, using the square root property, taking the square root of both sides, I'd get x is equal to either the positive or negative square root of 1, giving me x equals 1, or x equals negative 1. And so now I've got 4 solutions for that 4th degree equation. Thoughts? Shall we try another? This next example, let's look at 2x to the 2/3 plus 7x to the 1/3 minus 15 equals 0. This is sort of a fun one because, again, it's quadratic in nature. I've got a trinomial. One side is 0. It's in descending order. I have a constant term. And so now if I focus on the variable parts, looking at this is x to the 1/3. Well, if I double the exponent, I get x to the 2/3. So it fits that pattern. I'm going to let u equal x to the 1/3. And so u squared would be x to the 1/3 squared. And multiplying the exponents, that would give me that x to the 2/3. And so when I substitute, this becomes 2u squared plus 7u minus 15 equals 0. And by using that substitution, doesn't that equation look much easier to solve than the original? Again, we could use any method to solve this quadratic, but I think this one's pretty factorable. If I look at 2u squared, I'll have 2u and u. For 15, if I look at it as 5 times 3, if I put the positive 5 here and the negative 3 here, when I multiply, I'd have first 2u squared outer plus 10u inner minus 3u. And that 10 minus the 3 would give me that 7 in the middle. So we've got it. So now we'll set each factor equal to 0. On the left, solving 2u minus 3 equals 0. We can add 3 to both sides, giving me 2u equals 3. And then dividing, I get u is 3/2. On the right, where I have u plus 5 equals 0, I'll subtract 5 from both sides, and I'll get u equals negative 5. But again, I solved for u, and the original problem asks us for x. So going back up, we had said that u is equal to x to the 1/3. So when I substitute x to the 1/3 equals 3/2, and x to the 1/3 equals -5, we've now got those equations we talked about last week, where we have a rational exponent. And we had said to solve those, we're going to raise both sides to the reciprocal power. The reciprocal of 1/3 is 3. And so here, when I raise both sides to the third power, I get x equals 3 to the third over 2 to the third is 27/8. And over here, if I raise both sides to the reciprocal power, again, the reciprocal of 1/3 is 3, I get x equals -125. With this one, let's go through and do a check. Again, in order to check, we want to go back to the original, which was 2x to the 2/3 plus 7x to the 1/3 minus 15 equals 0. So I'm going to take 2 times 27/8 to the 2/3 plus 7 times 27/8 to the 1/3 minus 15. And we're going to hope that that gives us a 0. Well, we just saw that 27/8 is 3/2 cubed. When I raise it to the 2/3 power, I take the cube root and square it. So that would give me 2 times 9/4 plus 7 times the cube root of this would be 3/2 minus 15. So that gives me 9/2 plus 21/2 minus 15. For 30/2 minus 15 is a 0. So it checks. And then our other solution is x equals -125. And so when I take 2 times -125 to the 2/3 plus 7 times -125 to the 1/3 minus 15, again, I'm hoping to get 0. Again, we said that -125 was -5 to the third. So the cube root of that would be -5. Squared would be +25. So that's 2 times 25 plus 7 times, again, the cube root of that is -5 minus 15 is 50 minus 35 minus 15 is 0, and it also checks. So these equations that are quadratic in nature, we're going to make one side 0, have them in descending order, and then substitute for the variable part of the middle term. So, well, this one's sort of interesting. Let's have you folks try this one. Is everybody set? Can I turn the page? Next example, let's look at x to the -2nd minus x to the -1st minus 20 equals 0. Where we have a trinomial descending order constant term, one side 0. One exponent is double the other. So what should I let u equal? Any ideas? Anybody?
The negative first.
If u is x to the negative first, u squared would be x to the negative first squared would be x to the negative second. And so we can replace x to the negative second with u squared. We can replace x to the negative first with u, and our constant stays the same. I think that one's a pretty simple factor. How would you folks factor u squared minus u minus 20 equals 0?
Minus 4. Minus 5 plus 4.
U minus 5, u plus 4 equals 0. Great. And so then we can set each factor equal to 0. Giving me u equals 5 or u equals negative 4. But x to the negative first. So x to the negative first equals 5, or x to the negative first equals negative 4. So you could raise both sides to the reciprocal power. The reciprocal of negative 1 is negative 1. And it gives me x equals 1/5. Or here, raising both sides to the reciprocal power, I get x equals negative 1/4. And so that those would be our solutions. General idea with this u substitution, taking something that sort of looks like a quadratic, but not really, and rewriting it as a quadratic, and then putting it back in terms of the original variable when we're finished and solving. Everybody okay with these? Any questions? If not, the next type of equations that we're going to look at are absolute value equations. And when I look at absolute value, remember we had a two-way definition for absolute value. What would we do if we had a positive, or what would we do if we have a negative? But if I look at like the most basic, if I look at something like the absolute value of x is equal to some number, let's say 3. What's inside there? Couldn't x be 3? Or couldn't it also be negative 3? We're going to say in general, if the absolute value of x is equal to some quantity a, then with these absolute value equations, we'll have two possibilities. X could equal a, or x could equal the opposite of a. And so I like to think that when I look at that absolute value symbol, it's got 2 bars. And when I solve that absolute value equation, I end up having to solve 2 equations. One where the quantity in between the bars is equal to the expression on the other side, and one where it's equal to the opposite of that expression. So let's say I have an example like the absolute value of x plus 1 minus 3 equals 2. In order to solve an equation like this, the first thing that we want to do is we want to get the absolute value symbol alone on one side of the equation. So I'm going to say that we want to isolate the absolute value. So again, to get what's in between the absolute value bars, to get the absolute value bars alone on one side, is it clear to everybody we'd have to move that subtracting 3? So let's add 3 to both sides, and we'll get the absolute value of x plus 1. I apologize. X plus 1 equals 5. Now that the absolute value bars are all alone, we're going to rewrite as 2 equations. In the first equation, I'm just going to get rid of the absolute value bars. The absolute value of x plus 1 is 5. So for the first, I kind of think of just lifting the bars. And for the second, we're going to lift the bars. X plus 1 equals, and take the opposite of the second's other side. And so notice both equations, I'm not changing what's inside the absolute value bars. It remains the same. I'm just getting rid of the absolute value bars. On one side, that's all I do. On the other side, I have to change the side of the signs. Take the opposite, multiply by -1. Now we're going to solve. So on the first, where I have x plus 1 equals 5, I'll subtract 1 from both sides and get x equals 4. On the second, where I have x plus 1 equals -5, I'll subtract 1 from both sides and get x equals -6. And with these, we want to check all our solutions in the original. And I think that original equation was the absolute value of x plus 1 minus 3 is supposed to equal 2. So first, if I check x, my stylus just stopped working. Let me try it one more time. If I check x equals x equals 4, I have the absolute value of 4 plus 1 minus 3. Equals 2. So 4 plus 1 is 5. That's the absolute value of 5 minus 3. Which is 5. I'm so sorry, you folks. I have no idea why all of a sudden this thing doesn't want to work for me. This gives me 5 minus 3, or 2 equals 2, and it checks. On the other side, I'm going to check if x equals -6. That becomes the absolute value of -6 plus 1 minus 3. And I want to know, does that equal 2? Well, -6 plus 1 is -5. And the absolute value of -5 is 5. And 5 minus 3 is 2. And it checks. And so what you have to remember when you're solving an absolute value equation is you want to rewrite it as two equations. But before you do that, you need to isolate the absolute value, get it alone on one side of the equal sign. Shall we try a couple more? Next example, let's look at the absolute value of 2x. I'm sorry, this isn't what I want to do next. I apologize. Let's look at the absolute value of x plus 1 plus 3 equals 2. Then the first thing that we want to do is get the absolute value alone. To get the absolute value alone, we'll have to move the plus 3. So let's subtract 3 from both sides. Gives me the absolute value of x plus 1 is equal to -1. So now we'll make two equations. X plus 1 equals -1, or x plus 1 equals the opposite of -1, which is 1. Solving the first, let's subtract 1 from both sides. Gives me x equals -2. Solving the second, subtracting 1 from both sides, I get x equals 0. That one wasn't too bad. Let's look at our check, though. The absolute value of -2 plus 1 plus 3 has to equal 2. Well, that's the absolute value of -1 plus 3. 1 plus 3 is definitely not 2. If I try 0, the absolute value of 0 plus 1 plus 3, we want to know, does that equal 2? Well, that's the absolute value of 1 plus 3. 1 plus 3 also does not equal 2. So neither work. And so again, with these, the checks are important. However, did anybody notice anything way back here when we got the absolute value alone? Do you notice that we were saying that the absolute value is equal to a negative? Can absolute value ever equal a negative quantity? No. So I guess at that point we could have stopped there and said that it was not solvable. But if you didn't notice, you could carry on and finish the equation. But realize that this kind of puts an emphasis on why we need to do those checks. Next example, I'd like to have you folks try alone. Let's take the absolute value of 2x minus 3 minus 8 is equal to 3. And I'm going to be quiet for a minute and let you folks solve that one. Did everybody get their two solutions to be 7 and -4? And both should check. Does anybody have a question on solving an absolute value equation? Again, get that absolute value symbol all alone on one side, and then rewrite it as two equations. For each of the equations, on the side with the absolute value, we're just eliminating the absolute value bars. In one equation, we leave the other side alone. And in the other equation, we take the opposite of the other side. Any questions? If not, that's the end of the material that's covered in that section, 1.6. And so let's move on to that section 1.7 that involves inequalities. And I know that earlier on, we did look a little bit at inequalities. We said that our symbols for inequality were less than, greater than, less than or equal, and greater than or equal. We also looked at interval notation. And number line graphs. With interval notation, we said we had a pair of numbers. One was the lowest value, other was the highest value. And we had said that we could use soft parentheses, which would be like on the graph, open dots. If the inequalities were strict, less than or greater than. And we said that we would use closed brackets, which would be like on a graph, closed dots. And we'd use if we had less than or equal to or greater than or equal to. And we had said that we could also mix the symbols depending on whether we had a strict inequality or not on both sides. And so, for example, if I had an interval that was, let's say, closed at -2, comma, open at 4. We had said that we could picture this on a number line. If the lower limit is -2, the upper limit is 4. Because that's square, we could put a square bracket at -2, soft at 4. Or we could look at that as having a closed dot at -2, an open dot at 4. And we can consider all of the values in between. Or we could say that was -2 is less than or equal to x is less than 4. Does everybody remember looking at this interval notation earlier in the semester? Instead, let's say I have an example, an inequality. Let's say I have that x is greater than or equal to 8. Well, if I were to look at this on a number line, I've only got that single value, 8. It can equal 8, so that would be like having a closed dot. And if x is larger than 8, we'd take values to the left. Again, we had said those closed dots were like the squared brackets, and we're taking everything to the left. Or the smallest value is 8, and it can equal 8. Remember we had said if there is no larger value, we put that symbol for infinity, saying that it's going to just keep on going on and on and on and on. And we had said because infinity is a concept and not a value, we can't equal it. And so if we have infinity, we'll always have that rounded race. Does everybody remember this interval notation?
I vaguely remember.
Okay. Then beyond the interval notation, we also talked about set operations. And we had the union of two sets. The symbol was like a very stretched out block like uppercase U, and it combined all the elements from both sets. And we had the intersection of two sets. And the symbol for intersection was that union symbol upside down, and it was the elements common to both sets. And we talked about finding the union and intersection of intervals. And frequently, it's easiest to find the union and intersection of two intervals if we sketch the intervals on a number line. So for example, if I have something like the open at 0, closed at 7 interval, intersect the interval that's closed at 4 and goes on to infinity. One way of finding this is to sketch the first. And so the first interval is open at 0, closed at 7, and all the values in between. Then we'll sketch the second. And we'll try to have the number lines have the same spacing. So here I've got closed at 4, which would be in between 0 and 7. And then it doesn't stop. And then I'm going to compare the two. For the intersection, We want what they have in common or the overlap of the two. And so what the two share, let's see, they would overlap. They both contain 4. They both contain 7 and the values in between. And so the intersection would be the closed interval from 4 to 7. If we look at another example, let's look at the closed interval from 1 to 10 intersects the open interval from -3 to 5. Again, I like to sketch these. Closed interval from 1 to 10. We include the 1. We'd include the 10 and all of the values in between. Open interval from -3 to 5. Let's see, -3 would definitely be to the left of 1. 5 would definitely be in between those values. We're not including either endpoint, and we take all of the values in between. So now, if I look for their intersection, what they have in common, let's see, they both include the number 1. They overlap until 5. The first set includes the 5, but the second one doesn't. And so I would have my intersection be the interval that's closed at 1 and open at 5, and all of the values in between. So far, so good? Instead, if we look at the union, when we take the union, we don't want the overlap, but we combine all the elements of both. And so if I were to instead have 1, 10, union -3, 5, with the union, the first one again is values from 1 to 10, including the 1 and 10. The second one is values still -3 to 5, not including either. But now if I combine them, I don't want just the overlap, but I want everything from both. Well, when I put them together, the smallest value would be -3, which we're still not including. The largest value would be 10, which we are including. And we'd have all of those values in between. So my union would be the interval closed at open at -3, closed at 10. And one more union, let's look at the interval. Let's say we're from open at -1, closed at 2, union an interval that's, let's say, open at 4. Let's have this one go on to infinity. If I tried to picture those, the first one starts at -1 and ends at 2, all the values in between. The second one starts at 4 and takes everything to the right. Well, if I try to put these together on a single number line, wouldn't I just have those two disjoint intervals? And so here the solution would just be written. The interval open at -1 closed at 2 union the interval from 4 to infinity. When I take the union, I'm just combining the two together. When I'm taking the intersection, I'm looking for their overlap. I don't think we did much beyond sketching inequalities earlier in the semester. So let's go take a quick look at what we need to do in order to solve inequalities. And when we solve inequalities, they're very similar to solving equations in some ways, but in other ways, they're very different. When we solve inequalities, we're going to have a couple of properties that we need to use. One is the addition and subtraction property of inequality. And what they say is if I have an inequality, let's say A is less than B, if I add the same quantity to both sides, the inequality stays the same. Or for that matter, if I subtract the same quantity from both sides, the inequality stays in the same direction. So if you add or subtract the same quantity from both sides of an inequality, the direction remains the same. And so if I'm just adding and subtracting to both sides, it does work very, very much like equations. Let's say for an example, I have something like x minus 7 is less than 1. I'm trying to get the x alone, isolate the x. So I'm going to do the opposite to both sides. I have to do the same thing to both sides. The opposite of minus 7 is add 7. Those two are equal. But if I add the same quantity to both sides, my inequality remains the same. Make sure you keep your original inequality in there so that you know it's in the same direction. Another example, let's say instead this time I have x plus 9 is greater than or equal to 15. Well, to get the variable alone, I want to subtract 9 from both sides or add -9 to both sides. Because I'm subtracting the same value from both sides, my inequality remains the same. So if I'm adding the same quantity to both sides of an inequality, it works very much like an equation. Where it gets different is if I look at the multiplication and division properties of inequality. And I'd like to go through an example with numbers to kind of show you why this property holds. If I compare the numbers -3 and 1, is everybody all right? -3 is less than 1. A negative is smaller than a positive. if I multiply both sides, I'm going to do this side-by-side comparison by, let's say, 2. I'd have negative 3 times 2, and I'd have 1 times 2. Negative 3 times 2 is negative 6. 1 times 2 is 2, and it remains less than. Negative is smaller than positive. Instead, if I multiply both sides by, instead of 2, a negative 2, on the left I'd have negative 3 times negative 2. On the right I'd have 1 times negative 2. Negative times negative would be positive. And over here, positive times negative would be negative. And do you notice, because the signs reversed, the signs changed, we reverse the inequality. So with multiplication and division with an inequality, what happens is if you multiply or divide both sides of an inequality by a positive, the direction remains the same. Multiply by a positive quantity, the direction remains the same. But instead, if we multiply or divide, I'm sorry, I forgot the or divide, both sides of an inequality by a negative, the direction reverses. And that's where solving an inequality differs from solving an equation. If we multiply or divide by a positive, the inequality remains the same. If we multiply or divide by a negative, it reverses. So, does everybody have that down? Let's look at a couple of examples. First example, let's look at 2 times parentheses x plus 4, close parentheses, is greater than 3x minus 5. Just like with solving a first degree equation, does it make sense that I want to simplify each side first? And so to simplify, does everybody see on the left the need to distribute? I get 2x plus 8 is greater than 3x minus 5. Then we want to get all of the variables on the same side. In order to do that, we're going to add and subtract, and or subtract. So what would you folks rather do? Subtract the 2x from both sides or subtract the 3x from both sides?
Subtract the 2x from both sides.
So if I subtract the 2x from both sides, again, it's equal to, but because we're subtracting, the inequality remains the same. Now to get the x alone, we'd have to add the 5 to both sides. And the inequality, because we're adding, remains the same. And so we get that 13 is greater than, whoops, that should be an X, not an 8. I apologize. So here, the largest value is 13. There is no smallest value. So we'll have the open interval from negative infinity to 13, or we're not including the 13, X is on the smaller side, which would give us that same open interval. Instead, let's say I have 7 minus 3x is less than negative 2. Here, there's no need to simplify. I'm going to get the x alone. So let's subtract 7 from both sides. Gives me negative 3x is less than negative 9. Now this is where we have to be careful. We have that negative coefficient. So when we divide by that negative 3, because we're dividing by a negative, we have to remember that we reverse our inequality. And so we get that x is greater than 3. To show it on a number line, we have 3. We're not including the 3, and we want the larger side. So this would be an interval open at 3 to infinity. All right, for solving inequalities, this is familiar to everybody, where you have to be careful is if you multiply or divide by a negative. And if you do so, you have to remember that that direction switches. Then, next thing we're looking at are compound inequalities. And when I look at a compound inequality, it's where I combine two inequalities into a single one. Let's say I have something like negative 8 is less than or equal to 6 minus 2x is less than 12. To solve the compound inequality, what I want to do is I want to isolate the variable in the center of the inequalities. And I do that by adding, subtracting, multiplying, or dividing all 3 parts of the inequality by the same quantity. And so, as I look at this example, my variable 2x is in the center. I want to get it alone. In order to get that 2x alone, I would have to move the 6, and I'm going to do that by subtracting 6. And again, if I do that to any part of that inequality, I have to do it to all 3 parts. That gives me negative 14 is less than or equal to negative 2x is less than 6. Now, in order to get that variable all alone in the center, I would have to divide that coefficient of -2. If I do it to one part of the inequality, I have to do it to all three parts. And when I divide by a negative, I have to remember that the direction of my inequality is reversed. I'm left with x in the middle. On the left, I have 7. On the right, I have -3. So I've got 7 is greater than or equal to x is greater than -3. I could picture that on a number line, -3 and 7. My variable is in between. I am not including the -3. I am including the 7. So I'd have the interval open at -3, closed at 7. Let's look at -3 is less than or equal to 2/3 x minus 5 is less than -1. Again, we want to try to get the variable alone in the center. First, let's get that variable term alone. So we'd want to move the -5. The opposite of subtracting 5 is to add 5. And again, I have to do it to all three parts of the inequality. That gives me 2 is less than or equal to 2/3 x is less than 4. Now, in order to get the variable alone in the middle, remember, if we have a fractional coefficient, we want to multiply by the reciprocal. So I'm going to multiply by 3/2 because it's positive. My inequalities stay the same. And again, whatever I do to one part of the inequality, I have to do to all three parts. That leaves me with 3 is less than or equal to, here the coefficients would multiply to 1. X is less than, here we get 12/2 or 6. On a number line, we're looking at values between 3 and 6. We're including the 3, we're not including the 6. Everything in between, so it would be the interval from 3 to 6. How's it look? I'm going to be quiet and ask you folks to please solve the compound inequality. Let's look at 3 is less than or equal to 4x minus 3 is less than 19. And I'm going to give you folks a couple minutes to work on this one. Did everybody get the interval from 3/2 to 11/2, closed at 3/2, open at 11/2?
I did.
Great. Any questions? And actually now I'm looking, and I didn't think that we were going to get quite this far today. I had thought that the next topic is going to be left, was going to be left for Thursday, but I think we have more than enough time to look at those absolute value inequalities. So before we do that, I want to backtrack a little bit and ask your folks' opinion. Initially, I had thought that we would not get to the absolute value inequalities until Thursday. And so that homework is not due until next Tuesday. And I would have the test available for you folks next week from Tuesday to Thursday. And I'm wondering if you would rather have the test available from Thursday till Tuesday this coming weekend, over the weekend instead. It would be moving the test up, but it would be having it available for you folks over the weekend instead of just midweek. What are your thoughts? Would you rather have the test be available a week from today and open from Tuesday till end of the day Wednesday? Or would you rather take it sooner and have it available over the weekend? Any preferences?
I think I'd prefer to have it over the weekend if anybody else shares that same thought.
I'll tell you what we'll do is we'll make a quick poll and see what people think. If I can remember how to make a poll. Let's see. I'm sorry, it's taking me a minute. So you should have a poll in front of you. Test for test to availability. Do you want it this Thursday, the 18th, till next Tuesday, the 23rd, open over the weekend? Or would you rather have it open Tuesday, the 23rd to Thursday, the 25th, where it's a little bit further along and you can have a little bit more time before you take it? And there's 17 folks. And so, a lot of people have not yet voted. Do I take that to mean that you don't care or that you're not paying attention? All right, it's kind of like a 2/3, 1/3. Let's think about this for a minute. We could try to come up with a compromise. How would it be if we had the exam available from Friday, the 19th to Wednesday, the 24th. On Thursday, the 18th, we can just review, which would be going over a practice test. On Tuesday, the 23rd, we'll start the new material. But for those people who were hesitant to commit to the weekend, going on the assumption that you might, some people want it open over the weekend, but some people want more time. Does that sound like a reasonable compromise?
I think so.
Is that all
Repeat
right
that
with
for me?
everybody? Say that again?
Could you repeat that for me? Sorry.
Okay, but it's what I've got written here. On Thursday, because we should be done with the new material we'll review, we'll have the test open from Friday to Wednesday, because a lot of more people said they wanted it over the weekend, but I'm concerned with the people who didn't want to move the date up, that they feel they need the extra time with the material. And so it'll
Okay.
be available till Wednesday. And Thursday we'll review in class. Tuesday we'll start the new material. But if there are a couple last minute questions, we can deal with them. Does that sound like a
Okay.
compromise?
That sounds better. Sorry, I just couldn't hear it. I blanked out for a solid 2 seconds. Sorry. Thank you.
Okay. So everybody all right with that? So I'm going to cross this out and use that instead, and I'll go through and change the dates in my labs and in Blackboard on that test. But now the last type of inequalities that we're going to solve are absolute value inequalities. And we're going to find that there are two distinct types of absolute value inequalities that we have to solve. And the first type is to say the absolute value of our variable is less than some quantity A. Well, if I look at one of those definitions that we had for absolute value, was the distance from 0 on the number line. And so if the distance from X, whatever it is less than A, doesn't that mean I can go a distance A to the right, but also a distance negative A to the left? And so if the absolute value of x is less than a, wouldn't that tell me that x has to be in between negative a and a? Or for example, if I said the absolute value of x is less than 3, x would have to be a number smaller than 3, but it couldn't be smaller than negative 3, because when I take its absolute value, it would then become bigger than 3. So to solve something of the form, the absolute value of x is less than a quantity a, we're going to first isolate the absolute value. Then solve the compound inequality. Negative a is less than x is less than a. And so, for example, if I have the absolute value of 2x plus 6 over 3, all in absolute value bars, plus 1 is less than 3, the first thing that I want to do is I want to get the expression in the absolute value bars alone on one side of the inequality. In order to do that, I'd want to subtract 1 from both sides. And that leaves me with the absolute value of that fraction is less than 3. Again, because I added or subtracted, the inequality remains the same. Now, because that absolute value is less than, I'm going to rewrite as that compound inequality. Negative 3 is less than that quantity that we're taking the absolute value of is less than 3.
Shouldn't that be 2?
Thank you. It should be 2. 1 minus 3 is 2. I appreciate that. I guess I must have zoned out for a minute. Sorry, folks. And now, because there's a fraction there, remember with fractional equations, you wanted to multiply all parts of the equation by that common denominator. So I'm going to take all 3 parts of that equation and multiply by 3 to clear the fraction. Giving me negative 6 is less than 2x plus 6 is less than 6. Now again, it's a compound inequality. We will now get the x alone in the center. So let's subtract 6. And again, if I subtract it from any part of that compound inequality, I need to subtract it from every part, giving me negative 12 is less than 2x is less than 0. Realize we have to keep that third part of that inequality. We have to keep that less than 0. I sometimes see people do careless things. That less than 0 is important. And so now to get the x all alone, we'll divide everything by 2. It's a positive 2. So my inequalities stay in the same direction. And I get negative 6 is less than x is less than 0. If I were to look at it on a number line, we're not including the negative 6. We're not including the 0, but we're including every value in between. So it would be the open interval from negative 6 to 0. If we look at another one of these, let's look at the absolute value of 3x plus 5 is less than 17. And I'm going to be quiet and ask you folks to, because it's less than, change this into that compound inequality and solve. And tell me what you get. Did everybody get the open interval from negative 22 thirds to 4? Does anybody need any details? Any questions? Okay, because my absolute value is less than 17, that quantity can be less than 17, but it also must be greater than negative 17. To get the variable alone in the center, we need to subtract 5 from all 3 parts of the inequality, giving me negative 22 is less than 3x is less than 12. And then to get the x all alone with a coefficient of 1, we'll divide all 3 parts by 3. Because that's a positive 3, the direction remains the same. And we have the open interval from negative 22 thirds to 4. Everybody okay? Any questions? If not, then let's look at what happens if my inequality is in the opposite direction. What if the absolute value of x is greater than a? If we look at that on a number line, we're saying that the distance from 0 has to be larger than a. So if I'm further from 0 than a, I could be everything greater than a. But on the opposite side, if I'm further from 0 than a, wouldn't I be less than negative a? So if the absolute value of x is greater than a, then x is greater than a, or x is less than negative a, or we take x is greater than a union x is less than negative a. So to solve an absolute value inequality like this, where the absolute value is greater than, we first want to isolate the absolute value. Then write two inequalities. One where x is greater than a, and one where x is less than the opposite of a. So let's look at a couple of examples of these. Let's look at 4 plus the absolute value of 3 minus x over 3 is greater than or equal to 9. Again, we want to get the absolute value bars alone. So the first thing we're going to do is subtract 4 from both sides, which gives me the absolute value of 3 minus x over 3 is greater than or equal to 5. Now, because it's greater than 5, I've got to create two inequalities. One would be that 3 minus x over 3 is greater than or equal to 5. The other would be that 3 minus x over 3 is less than or equal to negative 5. And again, this one we cannot solve with a compound inequality, because with a compound inequality, I try to put those so that my symbols of inequality are in the same direction. I'd have 3 minus x over 3 is greater than or equal to 5, less than or equal to negative 5. And if I look at this, do you see that this makes absolutely no sense, because we're saying negative 5 is bigger than 5. So here we cannot use a compound inequality, and we have to solve the two inequalities separately. Solving the first one, where I have 3 minus x over 3 is greater than or equal to 5. First, let's get the x term alone by subtracting 3 from both sides. Gives me negative x over 3 is greater than or equal to 2. And now to isolate the x, we'd have to multiply both sides by negative 3. And remember, when we multiply by a negative, we change direction. And so we get that x is less than or equal to negative 6. On the other side, where I had 3 minus x over 3 less than or equal to negative 5. Again, we'd start by subtracting 3 from both sides, giving me negative x over 3 is less than or equal to negative 8. Then we have to take both sides of that inequality and multiply by negative 3. And again, because we're multiplying by a negative, the direction reverses. And I get that x is greater than or equal to 24. So I'd have x is less than or equal to negative 6, union x is greater than or equal to 24. Or including negative 6 and everything to the left, including 24 and everything to the right, or interval notation, we'd have from negative infinity to negative 6, closed at negative 6, union closed at 24 to infinity. So if it's greater than, it's further from 0, and we expect to have these two intervals going in opposite directions. So let's try a couple more. let's say I have 3 times the absolute value of x minus 1 is greater than or equal to 6. With this one, does everybody see the need to get the absolute value alone? We'd want to divide both sides by 3, giving us the absolute value of x minus 1 is greater than or equal to 2. Again, we're saying it's further from 0 than 2. So we're going to have 2 inequalities in opposite directions. X minus 1 is greater than or equal to 2, or x minus 1 is less than or equal to negative 2. Please notice that when I do this, I'm changing the sign on the side of the inequality that did not include the absolute value. What was within the absolute value bars remains the same. So now solving the resulting inequalities, I get x is greater than or equal to 3, or x is less than or equal to negative 1. So we would have less than or equal to negative 1 would be from negative infinity to negative 1, or is union greater than or equal to 3 would be from 3 to infinity. And I believe we have time for one more absolute value inequality. This time, let's look at the absolute value of 3x plus 5 is less than 17. And does everybody notice that because this one is less than, and my absolute value is alone, I'm going to say that 3x plus 5 is less than 17, greater than negative 17. And this one, because it's less than, I form my compound inequality. And so then to solve, let's subtract the 5 from each. Did we do this one already? This is looking vaguely familiar. Negative 22 is less than 3x is less than 12, and then divided. Negative 22 thirds is less than x is less than 4. You know what? I think I might have pulled the textbook up and accidentally copied one that I had already in the notes to do. So with these absolute value inequalities, you have to be very careful and make sure that you remember that if it's the absolute value is less than, you're going to solve a compound inequality, as opposed to if the absolute value is greater than or equal to, you have to separate it into 2 different inequalities. Any questions? If not, let's stop sharing. We've done an awful lot this section. What we will do on Thursday is review. We'll go over a version of the problem set, and maybe even a version of the test to make sure everybody kind of knows what to expect. You'll be able to take the tests anytime between Friday and Wednesday, but then next week, Tuesday, we'll start looking at that next section. Before we call it a day, I know that a few people came in late. Let's see. Did Joey come in? Kaya? Ellen Irene?